Hi, everybody. Today I'm going to talk about the voltage dividers, but before going through that topics, let's get started with some basic circuit. Uh, typical electronic circuit. So basically, you're going to have a circuit, and you have input, and you expect your output. And there's some technical term uh, has been decided here, and that's called transfer functions, as you may familiar with that before. That transfer function represented by capital H. That's become the ratio of your output and input, or you can say like the ratio of your V out and V in. Well, let's move forward. Go to the voltage dividers. That let's make it simpler then. In the case if you have the input voltage VCC, and then you have two resistors connected in series, and you want to find your output or V out, and that your V out is the voltage across your R2 in the circuit right here. For this case, the current flowing to R1 and R2 are equal because both resistors are connected in series. By Ohm's law, you will also be able to find the current flowing to the circuit. That means your current equal to the input voltage divided by the net resistance of your circuit. So in this case, it's the R1 plus R2. And you also know that the current flowing to R1 is equal to the current flowing through R2. And then your V out from the picture here, or from the circuit, that's going to be the voltage drop across resistor R2, or by applying Ohm's law. This means V out is going to be equal to I R2, and you know that your current is equal to VCC over R2 plus R1, or the net resistance of your circuit. So your V out end up with VC input or supply voltage multiplied by R2 divided by R1 plus R2. Now you can analyze the equation. In the case if you want to see how much your output voltage change when your competence change or varies. For example, if you want to find output voltage, how much the voltage change V out when your R2 varies, you can apply differential equation. So by differentiate your V out with respect to R2, you end up with 1 over R1 plus R2 minus R2 divided by R1 plus R2 squared. So from the notation here, the differentiate of your V out with respect to R2 means that you can find your output voltage, how much it change when your R2 resistance are changed by 1 unit, or in this case is 1 ohm. So you can do the same thing for R2 in the case of for R1 varies. So let's take a look at some example here. If I have a V input to be 20 volt, and you have 2 resistors connected in series. One is the 5 ohms and the other one is the 15 ohms. So you are looking for your output voltage. By applying the voltage divider equation, you have V out is going to be equal to supply voltage or input voltage, or 20 volt in this case, multiplied by R2, or 15 ohms, divided by R1 plus R2, or 5 plus 15, and you end up with V out to be 15 volts. So if you take a look carefully, you can see that the voltage drop across R2 is greater than the voltage drop across R1, and the voltage drop across R2 is actually your V out, or output voltage, and corresponds to R2 equal to 15, which is larger than R1, or 5 ohms. So your V out is proportional to your resistance, or R2 resistance. Okay, let's move on to the page number 2. I totally have 5 pages for this video. Okay, sorry, I should mention a little bit about the voltage divider. So it's obviously that your V out from the voltage divider is going to be less than the input voltage. In this case, you have input voltage is 20 volt, and you end up with the V out to be 15 volts. So it's no way for your V out is going to be greater than input voltage, except let's take a look back to voltage divider equation. Okay, from this equation. So to have V out to be greater than input voltage, or VCC, this means that your denominators have to be greater than numerator, or one of your resistor, either R1 or R2, has to be negative resistance. And in this case, it can happen in the case of, for example, using a tunneling diode, and then you have a negative resistance. So I'm not going to mention about the tunneling diode at this point. Now let's move to the page number 2. Okay, the next one is what I'm going to talk is about the voltage and the current source. Well, for the voltage source, you expect your V out, and you want to maintain your output voltage, which means that you don't want that change at all. It doesn't matter you have your load resistance or not. And for the load is attached to your output, sometimes your output voltage is going to drop, and you don't want that to happen. For example, if you have adapter for your laptop, your smartphone, you want to keep its output to be 5 volt. So when you connect that adapter to your smartphone or your laptop, you don't want 5 volts to drop, because you want to supply the voltage to your smartphone or your laptop 5 volts. That's just for example. So basically, to have the perfect voltage source, you want to maintain your output voltage to be fixed. Same as the current source. And for this one, for the voltage source, I give you an example of a battery. And the battery is like 9 volt, and have internal resistance or the source resistance to be 3 ohms. So you know that this battery can supply the maximum current to be 9 divided by 3 ohms according to Ohm's law. So that's give you 3 amp maximum current. Now take a look at the current source. It's the same thing, similar to the voltage source. For the output, you want to maintain the current, the output current, to be the same. You don't want to change that. It doesn't matter you have load connected to your current source or not. Now, there's one theorem that is very important, and many people are familiar with that. And this is the Thevenin equivalent circuit. What does this mean, Thevenin equivalent circuit? Well, Thevenin equivalent circuit means that, for example, if you have a supply voltage circuit, does include more than 1 resistors or more than 1 supply voltages. I just give you for example at this point. It is there to be easier for you to convert that kind of more complex circuit to be less simple circuit. What I mean is that we want to convert the supply voltage circuit to have only 1 supply voltage connected in series with a resistor, and only 1 resistor. Okay. And that the new supply voltage is going to be your Thevenin supply voltage, and you also have RTH or Thevenin resistor. Okay, so we will show you how to to find VTH and RTH as following. Well, let's take a look at some circuit. missed my point. That's page number 2. Oh, okay, sorry. Okay, let's take a look at the circuit. You have our input supply voltage, and you also have our R1 in series with R2, similar to the voltage divider circuit, as I discussed before. And this part actually is the supply, voltage. And this one is our load. For example, you attach load resistance to your supply voltage, or a laptop, or smartphone. Now let's analyze the circuit. So what I mentioned before is that we to make the circuit simpler, we have only one supply voltage and one resistor in the supply voltage circuit. So the way to look for VTH, or Thevenin voltage, and RTH, or Thevenin resistor, you can do by using some basic understanding. Your VTH is going to be V open. Okay, we need to take a look at the circuit. And your RTH, that's going to be equal to V open divided by I short. Okay, let's explain. What does it mean, V open? Well, for the V open, that means you have no load. So you have no load attached to the supply voltage circuit, or your R load. It's going to be infinity. So your V open circuit is going to be equal to V out, or the voltage drop across your R2. So by applying the voltage divider equation, you're going to have VTH equal to the supply voltage, or V in multiplied by R2 divided by R1 plus R2, and that corresponds to the circuit. Now for the I short, that means you short your circuit to the ground, from the output to the ground. Or that means your R load equal to 0. So the current is going to flow this way. No current flowing through R2. So your I short simply equal to the input voltage, or V in, divided by R1, and that corresponds to the circuit. Sorry, I'm missing this one here. Okay, so let's move on. Since there okay, then your RTH is going to be V open divided by I short, and your V open from the previous circuit is equal to V in multiplied by R2 divided by R1 plus R2, and your I short is going to be equal to V in divided by R1. So you end up with R1, R2 divided by R1, R2, or simply R1 in parallel with R2. So that's the net resistance. Sorry. So by take a look at the picture, you're at the circuit. You have R1, R2, and you have R load. So you can draw the Thevenin equivalent circuit like this. You have VTH and you have RTH, which is from R1 in parallel with R2, and you also have R attached to the circuit. Let's take a look at our sample. For example, you have R Vin equal to 30 volt. You have R1 equal to R2 equal to 10k ohms. Let's see the output voltage with no load attached, or in this case it's become V open or VTH, Thevenin voltage. So your V open is going to be equal to input voltage, which is 30 volts, and then multiplied by R2, and that's 10k divided by R1 plus R2. This means you have 10k plus 10k. So you end up with the open circuit to be 15 volt, and that's also apply VTH or Thevenin voltage. Next, let's take a look. If you have 10k ohms load attached to the circuit, what is your output voltage? Or in this case, you just take a look at your supply voltage circuit. You know that you're going to end up with your VTH. Sorry, this one is wrong. It's supposed to be 15 volt. All right, because you apply Thevenin theorem. And your R1 and R2 is going to be in parallel. So, sorry. Let's start over again. Sorry. I did something right. Well, just take a look at this one here. You have, this is your R load, and this is R2. So they are in parallel. You end up with the total to be 5k or half of 10k, and you still have R1, that's 10k ohms, in series with 5k ohm, and you want to look for V out. So your V out can be found from voltage divider. So your V out is going to be equal to input voltage 30 volt multiplied by 5k ohms resistor divided by 10k ohms resistor plus 10k ohms resistor, or R1. Finally, you have V out to be 10 volt. So by comparing A and B, for A you have no load attached to your supply voltage circuit. You have your V out to be 15 volt, and when you have 10k ohms load attached to the circuit, you have your V out to be 10 volt. It's obviously, you can see that your V out drop, a lot. If you consider that in the term of percent, you have the voltage drop from 15 volt to be 10 volt when you have 10k ohms load attached to the circuit. Now the Thevenin equivalent circuit. So you need to look for your VTH and RTH. But actually, you already calculate for your VTH or equal to V open from A, right? You have your V out 15-fold. And now to find RTH, that's equal to V open divided by I short. So let's take a look at I short, V short, the circuit to the ground. And that's one is I short is going to be input voltage 30 volts divided by R1 or 10k ohms. So you have I short to be 3 milliamps. So RTH equal to V open, which is 15 volts, divided by I short, which is the 3 milliamp, and you have RTH to be 5k ohms. So your circuit on the left, this is your first circuit, and then you apply Thevenin equivalent circuit, or you apply Thevenin theorem. You end up with your input to be 15 volts, and you have your RTH. Actually, sorry, I'm missing 5k here, and in series with 10k ohms load. Okay, that's how our Thevenin theorem works. Let's move to the page number 4. Now, as you define output voltage using our Thevenin equivalent circuit, okay, then you have a 10k ohms load connected to the circuit. So simply you apply the voltage divider, V out is going to be equal to 15 volt multiplied by 10k ohms resistor divided by 5k ohms plus 10k ohms, and you end up with the V out to be 10 volt when you have 10k ohms resistor connected to the circuit. So it's going to be the same as B that we worked out before. Let's take a look at the B. That's in the page number 3, I believe. Yep. So this is your V out. When you have 10k ohms load resistor connected to the circuit, you end up with your V out to be 10 volt. The same thing as you apply the Thevenin equivalent circuit. Next, power dissipated in each of resistors. Okay, starting from the circuit input voltage 30 volt, and you have the load attached to the circuit 10k ohms load, and by parallel these two resistor 10k and 10k, you end up with 5k ohms. You are half of 10k. So first you look for the current flowing through 10k resistor. Apply Ohm's law. So your current is going to be equal to 30 volts input voltage divided by the net resistance of 10k and 5k in series, and you have I equal to 2 milliamp. That means you have 2 milliamps current flowing through a 10 kilo ohm resistor, and then it's going to split. Since these two resistors are equal, so you're going to have 1 milliamp current flowing to 10K, and also you have 1 milliamp current flowing through 10Ks, or when you add them up, you back to 2 milliamps current. So if I apply the power dissipated equation, you have PR1 equal to R squared R1, and the current flowing to R1 or 10K ohms resistor is 2 milliamp. We end up with PR1 equal to 40 milliwatt. Now for R2, the power dissipated in R2 is going to be 1 milliamp squared multiplied by 10K ohms, or 10 milliwatt. Both are the same because they have the same resistance. Okay, that's all about our Thevenin theorem and also our Thevenin equivalent circuit. You may have heard about Norton theorem. Norton theorem is similar to Thevenin theorems, except we're talking about the current source, and you also have a resistor in parallel with the current source. But for Thevenin theorem, you know that you have one voltage source in series with that resistor, right? So there's some similar and some different. Okay, next. Now let's analyze circuit above, since we already do some work on how to calculate your V output with load or without load. From the circuit above, you have our input voltage 30 volt, and you have R1 in series with R2. Both are 10K ohms resistance, and you expect your V out. Well, when you have the load in the circuit, you know that your V out is going to be less than V out without load. So that's not good, because as I mentioned earlier, you want to maintain your output voltage. You don't want your output voltage to drop. So in practice, they overcome the problem, which I'm not explaining here, but it's just mentioned at this point. Maybe I explain that later. One is that you can use the much smaller resistor in the voltage divider or in the supply voltage circuit. And the other one is use the active components such as transistor or op amps. So later on we're going to discuss about transistor and op amps. Okay, let's go to the last page. Talking about equivalent internal resistance. If you take a look at the supply voltage, there's going to be some internal resistance, or somebody call like source resistance. For example, when you have oscillators, amplifiers, sensing devices, as we discussed before about the supply voltage circuit, if your internal resistance is greater or is about the load resistance, that's caused the output or the output voltage to drop. So that's not good. And that's what we call like circuit loading. So that's why we have to solve the problem or decide a circuit to maintain your output voltage. It doesn't matter you have the load or no load. Let's take a look at the plot for your R load much greater than our internal or the source resistance. On the exit, you have load resistance, and Y is the ratio of your V out over V open. V open, this means you have no load attached to your supply voltage circuit. So when your load resistance is greater, it tends to be the ratio of V out over V open tend to be 1, or they are the same. That means your output voltage not going to drop when you connected your load resistor to the supply circuit. But when your load resistance is lower, tend to be the ratios tend to be a fraction of 1. So that means it's less than 1. That's not good, because this implies that your output voltage drop a lot when load resistor is connected to the circuit. So to avoid unfolding the signal source, the open circuit voltage require R load much greater than our internal or the source resistance, source resistor. Okay, so I will explain the more details later on. All right, I'll see you in the next video soon. Okay, bye.